she explained the sort of organization and hierarchy, because it means I won't have to. I can skip a couple of slides and hopefully just take a few more questions. So yeah, very brief history of RISC-V. I will skip entirely because Helena covered it. And again, I think Helena and I must have stumbled on the same org chart to try and show all of this. So there's been many reorganizations of RISC-V as while I've been involved with it. The current structure looks as Helena describes, and we are the K crypto task group. Why it's spelled with a K, I feel like this is important to explain. C was taken. That is the compressed instruction set extension for RISC-V, and K happily overlaps with Kryptos, which was the original Greek meaning for hidden or secret, I think. So that's sort of a bit of serendipity there. So in terms of what the actual cryptography task group has been up to, so way back in 2018, it was founded with the brief to create large sort of AES-NI class instructions that would reuse the currently still work in progress RISC-V vector extension to do extremely high performance implementations of things like AES, SHA, and big integer arithmetic. And the cryptography world has changed since then in various different ways, as has the RISC-V world. So back in 2019, the brief was sort of expanded a little bit to include Scalar acceleration. So this is cryptography that is designed to run on microcontrollers. So you imagine your ARM Cortex-M4 class kind of device that everyone at Ches, I'm pretty sure, is quite familiar with at this point. And we sort of proposed that actually there's a whole big class of devices that don't have the space for big vector instructions, but can still benefit from sort of accelerated cryptography. And this would be something that RISC-V will be doing new that no other ISA has done. So this was added to the brief. And then in 2020, we kind of realized that actually the vector extension is so big, it's taking a long time to do. We'll put the vector extension for cryptography to bed for a bit, and we'll just focus on the Scalar crypto stuff. And that's why the Scalar cryptography specification has come out earlier. And it includes the spec for the entropy source. So this is where you generate your random keys. Secret keys from random values. So that specification is now out. It is ready. You can go and download it. I will give you all of the links later. And yeah, we're pretty proud of it. It's the world's first instruction set extension to provide lightweight cryptography accelerations. This means, kind of like Helena was saying a minute ago, because RISC-V caters to all class of device, from small embedded little microchips all the way up to allegedly big server class systems, you need cryptography acceleration for all of those kinds of device. And that can't really look the same for a server or a microcontroller. So because RISC-V is popular in the embedded space, we've started with embedded systems. So this is the PDF. You can find it on GitHub. Literally all our work is available on GitHub. So you can see you can't see my mouse, can you? Damn. Anyway, it's RISC-V crypto. This repository has the entire history of our work in there, including the specifications, benchmarks, modified tool chains, the whole lot. So we really weren't kidding when we say the work is public, which has lots of interesting side effects. In terms of what the Scalar cryptography extension contains, so we broke it into basically 3 components. The easiest ones to explain are a small number of very specific instructions for particular, very popular algorithms like AES and SHA-2. And I'm actually talking about the AES instructions tomorrow in one of the Ches sessions. So that, shout out, I guess. So yeah, the AES instructions we split in 2, one for 32 bits, one for 64 bits, because again, different classes of CPU, you can afford to specialize the instructions slightly to take good advantage. Instructions for SHA-2, and then SM3 and SM4, which aren't as well known, it's my understanding, but they are the Chinese standard equivalents of AES and SHA-2, and RISC-V being sort of an international standard, they merited inclusion on that basis alone. So these classes of instructions are designed to be extremely lightweight to implement, around about 1K NAND2 gates for those of you who are sort of more hardware focused, and you get an enormous speed up for your small investment in gates. And because it's a standard interface, you can write your crypto library to just look at these instructions rather than have to cater to all the different kinds of cryptography accelerator that different, your NXP or your STM32 microcontroller might support. So those are the sort of algorithm-specific instructions. But there's more to cryptography than AES and SHA, and we needed to keep the extension as generic as possible. And we did a whole load of research on what kind of instructions and operations would be useful for sort of basically other classes of block cipher or hash function. And happily, the bitmanip extension was already defining a load of these instructions. So rather than reinvent the wheel, we caused a whole lot of fuss with inside RISC-V by borrowing instructions from this other extension. And these include things like rotations, which frankly, you can't do a lot of cryptography reasonably without rotation, as we all know. And then you've got other sort of logic and not instructions that are good for bit slicing and SHA-3, and then some weird permutation instructions, which help various parts of SHA-3 or for sort of small S boxes. They're extremely quick and help with things like side channel, power side channel security, we hope, and I'll circle back to that a little bit later. But yeah, the emphasis from the start was always on algorithms which are already standardized and already very popular. So that meant things like post-quantum crypto or lightweight crypto, though important, and to some extent we can anticipate things like SHA-3 or Shake being useful for post-quantum crypto. We didn't actually go all in on trying to accelerate those algorithms yet because we've got to wait a little while for the standards. So that's why what's in there is in there and what's not in there is in there, if that makes sense. And then the final component is the entropy source. Far and away one of the most difficult parts of the specification, because we had a lot of sort of past designs to learn from people like x86 and ARM, and a lot of design mistakes. There's an impressive amount of literature about how people get entropy sources wrong. The selling point of the RISC-V entropy source is that it works with the same interface across microcontrollers all the way to servers. So I won't spoil the thrill of reading the technical specification for you. Suffice to say that if you're interested in entropy sources, it's a really good thing to start looking at right now. The advantage from a sort of commercial side is it's been designed to work perfectly with the new FIPS 140-3 certifications, which came out this year. So if you want to sell to the US government or people to take your cryptographic product seriously, you need it to be FIPS certified or Common Criteria certified. And this spec was designed to be that way from the start. So a lot of people have been sort of fans of it from that regard. And then a sort of meta component. So cryptographers love constant time. They love instructions that randomly break their assumptions about how computations work and whether or not they are data dependent. And we have defined a mechanism for CPUs to tell software, I promise that all of these instructions under certain conditions do not have data dependent latency. There are a few more caveats to it. It doesn't stop you being willfully silly, like doing secret dependent branches, but as long as you write your code in a particular way, it means you can make fewer assumptions about your code being constant time, which again, it's a first. Like no other ISA has this capability to sort of tell the programmer that, yes, it's safe to do a multiplier on my platform because the multiplier is constant time, to take a basic example. So it's got some interesting parts, and that's a very, very quick overview of everything that's in the extension. So the short-term roadmap is to get it all ratified in December. There's a big, the RISC-V Summit is a big yearly sort of jamboree of everyone involved in RISC-V, and it's there that the board of directors meet and vote to accept things. Allegedly, it's a rubber stamp, but I intend to go there and lock them in a room until they actually ratify our extension. And then we'll be moving back onto the vector cryptography stuff. So this is about taking getting the sort of more high performance instructions together. We have a fairly good idea of what those instructions will look like, but by the time December rolls around, we'll hopefully have NIST telling us which post-quantum algorithms have become standardized. So there's scope for looking at what new instructions or which other instructions that already exist would we want to include in a cryptography extension. And then the final component is what we're doing right now. It's pushing RISC-V into the community, so that researchers and industry know that as a platform for sort of security-oriented products, RISC-V is a really good starting point. So that's the short term. Medium and long term, well, post-quantum is going to be around. That transition isn't going to happen overnight. So we want to look at things like efficient implementations of it on RISC-V specifically. A lot of the previous work that I've been aware of has mainly looked at things like ARM and x86. So there's a lot to do there on RISC-V. The NIST Lightweight Cryptography Competition has, in my humble opinion, wrongly picked only one sort of benchmarking platform, the ARM Cortex-M4, what happens if you put these things to RISC-V? Does NIST's evaluation criteria completely change? This would be an interesting thing to look at. And again, a lot of these algorithms, they're being designed explicitly with sort of side channel security considerations there. How do those translate across RISC-V? These are a lot of really interesting questions. And then more generally, we want to produce things like advice and guidance for people. How do I do an efficient X on RISC-V related to cryptography? And that's slightly less technical, but more just making sure that people don't have to reinvent the wheel. And we want your help. Does this align with your research? Are we missing anything? The reason I got involved with RISC-V in the first place was because I thought, oh, there's a gap here. We can do fast cryptography for small devices, and if you offer to do some work, they will take you up on it. So bear that in mind. And yeah, it's basically, yeah, okay. That was easy. So in terms of getting started, how do you actually get involved and start looking at this extension? Because it's very new. There are no chips you can buy with it in. The first place to go is our GitHub, which I've mentioned already. You can see the spec on the right there, and then everything else is pretty self-explanatory. But this has everything in it that you need to get going. We also have a wiki, which is linked to there, which sort of basically it gets updated weekly with everything we've done in the last week or so as a task group and where we're going in the short term. This is mostly used by the people who manage the RISC-V standardization process, but it's quite good as a sort of at a glance. These are all the known implementations. These are all the example codes, that sort of thing. And then, yeah, like Helena mentioned, all the mailing lists are public. So you can view this just yourself normally. If you want to actually sort of subscribe and join in. Oh, that's terrible. They always turn up when you're in the middle of a meeting. Sorry about that, folks. My blooming doorbell. Where was I? Oh yeah, the mailing list. It's all public. If you want to join, it's free for academic members, which I think probably accounts for a lot of the chess crowd. So you've really got no excuse not to get involved. The actual links for these, we'll make sure that you have the slides later on. So those are all the sort of direct links to the slides that I just showed you. And yeah, like I say, what we're actually looking for is efficient implementations and guidance on how to do that, novel uses of RISC-V, sort of the existing instructions and new instructions. There's a high bar for introducing new instructions, but we've shown that you can be novel and introduce them. It's been, it's one of those things that's sort of making RISC-V a bit different from things like ARM. And yeah, what other things are we missing? We'd like to hear from you, basically. So that's been quite a whistle-stop tour of the extension. I have no idea how I'm doing for time, but I hope there's still time for questions. So yeah, thank you very much for listening. And I will stop sharing. God, that was exhausting.
So you're well ahead of time. We've got plenty of time questions, and there's a few flooding into the chats. So I don't know if you can see the chat, Ben, but let me read them out anyway. So Marcel asks, did I understand correctly, RISC-V with the crypto extensions provides guarantees about the constant timeness of assembly language instructions?
Yes, so it can provide that guarantee. It basically, for a subset of common RISC-V instructions, which are known to be useful for cryptography. So that's everything from sort of rotations to shifts to bitwise operations to integer multiplies. If the CPU vendor has implemented the constant time extension, there's a way to interrogate that, and you can be sure that your particular RISC-V core has a constant time multiplier, or won't undermine your assumptions that way. It doesn't cover things like caching. It doesn't cover loads and stores, and it doesn't cover branching on secret values. So it doesn't cover the really dumb stuff, but some of the more subtle things that can undermine your assumptions, that it's got you covered, yes. And this is new, so we want people to sort of use it and interrogate it, like, have we done a good job about defining that? Yeah.
So I guess that kind of touches on a follow-up question. So Mike H asks, has data-independent latency been formalized? At least when I tried to formalize this property, the statement ended up including also the CPU is not vulnerable to Spectre.
Yes, so we have quite a narrow definition of data-independent latency because we are only dealing with individual instructions. We're not dealing with the wider execution apparatus of the processor, like reorder buffers or branch predictors or anything like that. Our definition is simply that regardless of the inputs to the instruction, so the values going in the registers, this instruction will always take the same amount of time to execute in terms of latency or throughput. There's no like early out mechanism or whatnot. So we have quite a narrow definition. It wasn't designed to get around issues like Meltdown and Spectre. It was really just starting with the basics.
So a question about the entropy source. Boan asks, will the entropy source of RISC-V stick to or rely on one random physical phenomena or be open to other noise sources compliant with some rules?
The latter. So we don't care where you get your entropy from. We do care that the entropy is of sufficient quality, and we link to various different standards and sort of industry bodies about the quality of the entropy requirements. But whether you get that from something like a ring oscillator or various other sources, I forget them exactly. Ring oscillator is the easy one for me to reason about. Yeah, we don't mind as long as it's of high quality.
So I guess the difficulty there is the remit of being an instruction set versus kind of straying into the implementation of that.
Yeah, that is difficult. And the thing about an entropy source is, of course, it only takes one person to implement a bad entropy source before the rest of the RISC-V name is tarnished. So we're sort of expecting people to look at the particular CPU they're running on maybe and say, do I trust this entropy source? We're also hoping that market forces vigorously punish anyone who puts out a bad entropy source. Yes.
Okay, so there's a few more questions. We've got plenty of time, so I'm just going to keep asking them.
Sure. Yeah, I've dug myself this hole. That's fine.
So Alexandra asks, regarding the vectoring instructions, do you plan to make them work on extended size registers like ARM Neon?
So yes, without being an expert on ARM Neon, the RISC-V vector extension is quite different in the sense that it is designed to work on any unknown length of data with as long as you write your code in a particular way. For the AES instructions, which are probably the easier ones to sort of imagine, as long as you can do 128 bits of input, you can do a whole sort of 256 bits because you've got to get the round key in there. Yeah, we're expecting to have an instruction that does a whole round's worth. And if you've got vector registers that are 256 bits long, you can do 2 separate instances of AES at once. And I think the RISC-V vector registers can go all the way up to being like 4K bits or something crazy. So yes, the idea is to make it work properly with the vector extension.
Sylvie, I guess the question here is basically to provide a bit more detail about what the vector extension supports in terms of instructions and constructions based on those. So for example, does it support elliptic curves, I guess?
Yeah, so a lot of our work will be looking at the existing RISC-V vector instructions and making sure that they are appropriate for whatever sort of public key crypto or asymmetric crypto that you're trying to do. Because the last thing we will actually want to do is define new instructions. That's a pain for everyone. So if we can do it well with the existing instructions, and I think the common consensus is that we can, we will simply put guidance in to say, these are the instructions you should use. And hey, by the way, we've got a constant time extension that you should factor into your considerations, because the vector extension, doesn't necessarily get included in our current constant time extension. So we might define a new version for that. I think that answers your question. If we need new instructions because there's a particularly fiddly thing that will get you a big speed up on something like a post-quantum algorithm, we'll consider it. Yes. Yeah.
So I've got a quick question related to that. You mentioned that adding instructions was a pain for everyone. And I think that there was a high barrier of entry to selecting. So maybe you could say a bit about how that decision-making process works, because I could see that's one area where you get some translation from output that appears in shares into sort of standards maybe.
Yeah, so it's it's easy to propose an instruction for cryptography. The challenge is getting it accepted into a system that 99.9% of the time doesn't do any cryptography, right? RISC-V is a general purpose architecture. So if you want to add the Keccak accelerator instruction, that's great, but most of the time you're not doing Keccaks. So is that cost worth, is the performance increase you get from that worth the cost? And you've got to convince an awful lot of people, not all of them cryptographers, most of them not cryptographers, that what you're doing is worthwhile. And then you've got other considerations like, say you've implemented your instruction and it works great on your FPGA, but you're only running your FPGA at sort of 50, 100 megahertz. Well, someone in the RISC-V space will ask you, okay, what happens if I try and implement your instruction with my CPU running at a gigahertz? Is that instruction really implementable in that sort of performance envelope? Basically, there's a whole other bunch of considerations that come very much from the sort of industrial computer architecture space that the crypto community doesn't necessarily engage with all the time. And that's just the implementation side. Then you've also got to verify the instruction. Is it correct? Can you verify that it's correct? These are all various different challenges when it comes to getting instructions accepted to RISC-V. And it helps when you come to us that you've got an answer. I certainly didn't have all those answers when I started engaging with RISC-V, and it was a heck of a learning curve to sort of go, oh gosh, okay, these are the extra things I've got to think about. Yeah. Oh, and while I'm at it, RISC-V really does not like instructions that source more than 2 registers. They really do put the R in RISC. So for those of you who want to have loads and loads of inputs to your instructions, that is a great way to sort of make everyone shout and get scared. Yeah.
Okay, good to know. So I think that's about it. Let's maybe say thanks to Ben and move on to the next talk.